out the notes. No
Oh,
worries. All looks good.
all right. Well, thank you very much for the invitation to give this talk. I'm honored to be here. This is going to be a lot closer to home than a lot of these other presentations, but here I'm going to be focusing on the in situ measurements of galactic cosmic rays just outside our stellar astrosphere made by the two Voyager spacecraft. And the reason I'm here giving this talk is because I was the last graduate student of Ed Stone, and I did my first thesis at Caltech was on perhaps the first measurements of in situ kind of measurements of interstellar space. So it was the first thesis on that topic in cosmic rays. And and when I joined that team, it was around the time, it was 5 days after Voyager 1 crossed our heliopause. And so it's very neat to see this whole story unfold on the Voyager mission. So I will be talking about that here. And so the Voyagers, just to give a timeline, were launched. It's quite remarkable. It's almost been 45 years since they were launched, the two spacecraft, and it started out as the planetary mission, which I'm sure most people are familiar. But after the last image, in the 1990s, basically it became an interstellar mission, and the goal was to measure what the boundaries are of our heliosphere. And so there's a solar wind termination shock, a supersonic kind of a shock where supersonic solar wind slows down and it then becomes subsonic. So the termination shock is that boundary. And then there's a heliopause where the solar material basically pressure balances with the surrounding interstellar materials. And so starting in the 1990s, after the last flyby, basically was the beginning of this trying to understand what our boundaries are, how large is our heliosphere in the context of kind of the surrounding interstellar medium. And so Voyager 1 crossed the heliopause in 2012 in the centennial year of the discovery of cosmic rays, actually, very appropriate. It crossed in a direction 35 degrees above the solar ecliptic plane. And then 6 years later, Voyager 2 crossed about 30 degrees below the ecliptic, basically. And they're still sending back all their remarkable data. Voyager 1 is now 157 astronomical units from the sun, and the heliopause is about 120 astronomical units. So it's like the distance from Earth to Neptune, basically, beyond the heliopause. It was Voyager 1. And then Voyager 2 is now at around 130 astronomical units from the sun. And that's distance from here to Jupiter beyond the heliopause. And it's quite remarkable. It's a 43-hour round trip light time. And I'll begin on the discussion of cosmic rays with one of my favorite plots from the entire Voyager mission, which just reflects an incredible achievement of measuring cosmic rays through the entire heliosphere. And so this time axis reflects basically coincides also with the radial distance. The two spacecraft were launched around the same time, just a month apart, but at different speeds. So Voyager 1 goes roughly 3.6 AU per year, and Voyager 2 is a little slower, 3.3. But here you can see the effects of solar modulation on cosmic rays. Here's solar activity cycle on the bottom, referenced at 1 AU. And then here is kind of what they observed, the Voyagers observed, and you'd see the effects of the solar cycle and solar modulation, but it also weakens as the Voyagers traverse farther out through the heliosphere. And so when there is a crossing from the supersonic solar wind, which is right up through to these dashed lines, you can see that there's a radial gradient and strong effects due to the solar modulation. But then once they cross the termination shock, here Voyager 1 in red at TSX and Voyager 2 in blue, once they crossed termination shock, those effects kind of disappeared and it just became more dominated by a radial gradient. And very strong gradient. And then finally, when the Voyagers crossed the heliopause, which were very different times, Voyager 1 crossed as abrupt crossing took less than a day, and Voyager 2 was a little more gradual. Basically, the interstellar kind of measurements become very steady, very uniform. And compared to all the activities that we've seen of these lower energy cosmic rays being filtered by the sun, the interstellar medium is a quiescent place. And so hopefully I'll be conveying to you basically that it's not as boring as all this, but it is also full of some surprises. And so, but it's a lot different than our whole story of observing cosmic rays in these low energies of being filtered by the sun. And so here is a plot of what occurred after, right at the Voyager at the heliopause crossing for Voyager 1. It's a Voyager Cosmic Ray subsystem instrument that's designed, optimized for cosmic rays. And you see these particles dominated by cosmic rays basically had a sudden increase in their intensities, while the particles of heliospheric origin kind of suddenly dropped out. And here's a heliosheath, here's a very local interstellar medium. And these rates have continued very uniform to persist uniform even to this day. And around the time of the crossing, the magnetic field strength suddenly increased, which was what people expected for the interstellar values. But there's a big puzzle because the direction didn't change, and people expected the direction to change. And it looked very similar to what has been observed kind of as Voyagers were exiting and transitioning through the solar wind into the heliopause. So people were confused about that. There's also a very interesting correlation. It kind of crossed the boundary 5 times, Voyager 1 did. And there was a correlation where the anti-correlation really, where these are the particles, these are heliospheric particles, where they dropped out and the magnetic field strength increased. And there were kind of 5 of these boundary crossings. And that's since been explained as being from embedded flux tubes. So solar interstellar material embedded kind of as within the heliosphere and within the heliopause at the crossing, basically. And then it was a big question though, had we actually crossed the interstellar medium, or had we arrived in just some place that was depleted of all the heliospheric ions? And it turned out that that these fortuitous measurements of plasma density told us that we were in the interstellar medium. So Voyager 1 doesn't have a working plasma instrument. It failed at around Saturn and the Saturn encounter back in the 80s. But it turned out that there were radio emissions generated by plasma beam electron instabilities that the radio instrument picked up. And that is proportional, the frequencies of those emissions is proportional to the plasma density by this equation here. So it was a nice probe of what that plasma density is, and it was much closer to the expected plasma density. And so it was basically a closed story there of people saying that we have arrived in the very local interstellar medium. And that's the term I'll be using here. We refer to it as kind of that medium, different than the sort of astrophysical definition, which is many parsecs from the sun. Here, we refer to the very local interstellar medium as kind of the region where the material surrounding the sun is still modified by the sun itself, or heliospheric processes mostly. And so on Voyager 1 crossed at 122 astronomical units. Voyager 2 crossed at 119. They had different magnetic field strengths because the draping of the heliospheric magnetic field, of the interstellar magnetic field around the heliosphere, that draping compresses the field towards the Voyager 2 direction. And so it's a stronger field strength. And it was also very interesting in Voyager's measurements, there's evidence that the heliopause was likely shrinking as Voyager 1 crossed and likely expanding as Voyager 2 crossed. And so it's also not just a fixed boundary, it's changing with the output of the sun, the heliopause and the termination shock. Both those boundaries change and breathe a little bit. And so to summarize, here's a comparison of Voyager 1 and Voyager 2 with the crossings. And here you see in the red, the embedded flux tube kind of behavior, and here in the blue, you see kind of a very gradual ramp up. So this is kind of the evidence where where it was the heliopause, we think, is expanding, and that's why there's a kind of a gradual kind of change in the middle. In this middle panel here, you see that the blue kind of jets out a little longer, took a longer for the heliospheric sort of ions, anomalous cosmic rays and solar wind ions to escape compared to Voyager 1. And here's kind of the similar perspective on the low energy charged particle experiments on both spacecraft. And it's also cosmic rays, but they measure much lower energy of ions from the heliospheric, the yellow heliospheric material. And then the green is the galactic cosmic rays. But at this boundary, it opened up a very important question about what the where is the solar modulation boundary, and how to explain the very sudden crossing. And most of the models expected some sort of kind of a roll off, so that solar modulation may occur, the boundary may occur some distance away from the heliopause. But it turned out that this intensity change was very abrupt. It was within a day time scale. It's actually a time scale that's very difficult to resolve and explain with models. There's no radial gradient beyond that. So it looks like the heliopause is distinctively the solar modulation boundary. But it is still a surprise because at least so far, the best that models can explain is that requires the ratio of the parallel to the perpendicular diffusion coefficient from the heliopause versus from the interstellar medium versus the inside in the heliosheath inside the solar plasma. That ratio has to be 10 to the 10 or very many more orders of magnitude larger, I guess. So people are still trying to understand, why is this? What is causing this dramatic difference in the solar material versus very local interstellar medium in this diffusion coefficients, for example. So that's an interesting finding that the Voyagers discovered, and there's still more work to be done on that. But another really important result was the first measurements of the very low energy interstellar spectra. Even particles below a few hundred MeV don't even make it all the way into 1AU in the galactic cosmic rays. They get dominated by solar material and not even and filtered out in their journey through the solar wind. And so these were the first measurements of, in here in blue and red in these dots down on the low energy end, these first measurements of the low energy spectra. And then these black lines kind of towards the upper end of the plot show what the spectra was inferred from kind of Pamela measurements and other measurements at 1AU that aren't as affected by solar modulation. And so, one of the surprises, for example, is that the electron component at the low energies dominates actually by many orders of magnitude higher than the hydrogen and helium. And then the hydrogen and helium show very, very similar shape in terms of their roll off. And there's questions about, is this an unmodulated spectra, or kind of what does this represent? And what I would say is it's quite remarkable. There's no radial gradient so far observed by the Voyagers, no radial intensity gradient, no changes in intensities as function of distance from the heliopause, but also the two spacecraft are in their very different locations, north and south of the ecliptic, and they see a remarkably similar spectra. So we think this does kind of represent the very local interstellar spectra. And then if that was the whole story, it's very valuable contributions to the understanding of cosmic rays. And this outer boundary has actually led people to understanding the cosmic rays at just beyond the heliopause, led people to understand and refine their models, because it has an outer boundary. We now have an outer boundary condition to feed into for the spectra, for example, and propagation models. So that's been a very important set of contributions, and it would be a fine set of contributions, but there's also a few more surprises. So that's what I'll get into in the second half of this talk. so as I described, we see very uniform intensities of galactic cosmic rays beyond the heliopause. So the heliopause crossing was in 2012. So that jump up in the line on the left-hand side is the crossing of the heliopause, and then it was uniform and fairly steady. And these are measurements made by the low energy charged particle experiment, and it's on a stepper motor platform that has a 45-degree wide kind of viewing sector. It's a bidirectional telescope, and it just kind of steps in 45-degree segments basically, and sees in all directions with respect to the magnetic field. And the magnetic field is largely unchanging over this time period because the undraping of the interstellar magnetic field is very gradual. And so it turns out that in the sectors kind of parallel to the magnetic field, uniform rates in the sector 45 degrees with respect to the magnetic field, fairly uniform. We see a few little kind of jump ups, some little spikes here in intensity, and those are caused by some transient events I'll describe. But in the sector 90 degrees with respect to the magnetic field, there are these strange variations that occurred over a long time scales. So like this first episode occurred over kind of almost, well, 2/3 of a year, and this other very large one occurred longer than a year. And so there's these strange variations in cosmic rays as a function of pitch angle. So to summarize, this plot basically kind of shows these variations, but basically there's a dropout or a selective energy, I guess, decrease in cosmic rays having near 90-degree pitch angles. And it turns out that there's a detailed study where so the cosmic ray subsystem can't really see directly in the same way because it has body fixed telescopes. So it basically sees the omnidirectional kind of counts, but it doesn't see it in its directional telescopes unless in the bottom is the directional telescope, unless the spacecraft is performing a magnetometer calibration role. And so we actually took advantage of all those magnetometer calibration roles and the narrower field of view of our telescopes to actually show here in the next plot that the dropout is in fact centered on 90-degree pitch angles. And in a detailed study, we showed that it's this region of space that is roughly 20 degrees wide in pitch angle space. Maybe 15% of the particles within that region drop out and are responsible for are reflecting these events here. And an important finding we had related to that is that it's a species dependent effect. So here in panel B, we see electrons compared to protons during these distinct periods where the spacecraft has these offset maneuvers that points our telescopes towards the 90-degree pitch angle direction. And electrons of various energies do not see the effect, but the protons do. Protons of various energies do. So the black is protons with the average, it's greater than 70 MeV rates, but it's average of 500 MeV is the mean energy of these particles. And but even the lower energy protons in this panel D here in blue, 18 to 70, see these effects while the electrons do not. And so it's a puzzle what is happening out there. But a leading theory says that there could be a result of trapping within some interstellar shocks that are observed to occasionally occur, and from solar caused transients. And the idea is that perhaps particles get selectively trapped downstream, as illustrated by this figure on the left-hand side. The red is the compressed magnetic fields, and then they adiabatically cool downstream of the shock. And so the story is that the trapping of the 90-degree pitch angle particles causes them to lose energy in a way that's that they're not lost for other particles that can just escape this trap and not be adiabatically cooled. And so in the right-hand figure on panel A is again the cosmic ray intensity variations caused by this pitch angle anisotropy, and B is the magnetic field. And so, and these green lines indicate times when there's a forward or reverse shock that occurred. And then these blue lines indicate when electron plasma oscillations occurred. And I'll get to those in a little bit. But in this first event here, starting in 2013, you can see that there's a rise in the magnetic field along with the rise in cosmic ray intensities. And then as the magnetic field's enhanced, that's the time where the cosmic rays should lose their energy in the adiabatically expanding fields. And then when the magnetic field around 2013.4, when the magnetic field becomes a lot more uniform, there's a recovery in the cosmic ray intensities. And that works for this first event, but it's very difficult to understand exactly what's happening for these other events. So for example, in 2016, the magnetic field seems like it's still locally decreasing, and yet, and perhaps adiabatically expanding, and yet in 2016, this event starts to recover. And so we are not 100% sure what's happening here. Leading theories say it's this adiabatic cooling effect, but it's not necessarily local to Voyager. And so there are some indications that perhaps the draping of magnetic fields around the heliopause play a role in trapping, because in order to have trapped particles, you have to have enhanced magnetic field on either side with respect to the spacecraft. And so perhaps some of these disturbances past Voyager and when Voyager's downstream, perhaps it should definitely see these particles, but perhaps Voyager might not be downstream of the shock. And so there's some questions about how are these effects influenced by the large scale structure of the heliosphere. And then the last kind of very fascinating finding that Voyagers have been making out there is that the magnetic field and the plasma and cosmic rays also get largely influenced by solar activity. And it's strange, it's not solar modulation, but pileups of events like solar flares, CMEs, things that can coronal mass ejections and shocks basically traveling at different speeds. By the time they propagate out into the outer heliosphere, they can pile up and they can form these large events known as global immersed interaction regions that can transmit pressure waves from the heliopause into the very local interstellar medium. And so here is the view on the top panel of magnetic field, and these disturbances of shocks and pressure fronts, basically from solar related transients that just transmit these waves into the interstellar plasma, basically influence this whole particle environment. So particles, magnetic fields, plasmas, all of these get influenced by these solar transients that move outward. And so the shocks are kind of unusual and they're very weak, but they do cause electron plasma beam instabilities that basically are analogous to radio bursts seen in the solar wind by large CME events, for example. And so this is observed in the interstellar medium, and that's what caused these plasma emissions, and people were able to infer the plasma density out there. And it's seen in Voyager 1, which is this top, and then Voyager 2, which is this bottom. But it also turns out that the cosmic rays get energized. And so, in fact, there's a model that says that as Voyager is encountering one of these events, one of these shocks, basically once it comes into a magnetic field, crosses a magnetic field that's in contact with the shock, the highest energy particles get accelerated first, and then lower and lower energy particles. So at point A on this left-hand side, you see cosmic rays, which is what we observe first. We see these enhanced spikes in colored, these colored lines of enhanced spikes on the right-hand side. Those are energized cosmic rays from the shock. And then right before the crossing of the shock itself are the electron plasma oscillations, which occur at much lower energies of 20 to 100 eV, and then the shock itself. And so we're seeing this interesting aspect of shock energization in a plasma environment that is much different than we've observed so far in the heliosphere, for example. And it's a very quiet and textbook sort of environment to be studying cosmic rays and acceleration and these sorts of processes, even though they're somewhat weak compared to other things that we've observed. And that occurs at Voyager 2, and it's exciting time to be able to understand from these two perspectives what is happening out in the very local interstellar medium. And it's also an era of multi spacecraft observations through the heliosphere. So we're very close to being able to track these sorts of events from their origins on the sun all the way out to where they're impacted. And people have been studying this for a while on the Voyagers, but now we have some interstellar examples. So on the left-hand side, inside from when the Voyagers were inside our heliosphere, they saw these radio emissions from very large GMER events after they crossed the Voyager. So in some sense, it's not a surprise that these are making their way all the way out into the interstellar medium. And there's evidence of kind of, even in the heliosheath, of these events making their way. But it is a surprise that they affect cosmic rays the way they do. And so I guess because we're running out of time, I will leave with our conclusion here that this is a very exciting new regime. There are observations of all sorts that we can't fully explain, especially for the cosmic rays, especially for the pitch angle anisotropy. But it also takes understanding the whole context of observations on the Voyagers to be able to resolve these questions. And so I'll leave you with a summary slide. And thank you very much.